Assalamualaikum and hi everyone. My name is Muhammad FIRAS Hadi bin ZURAIMI and my metric number is 229527. Today, I will explain a real-life application of differential equations in an RC circuit. Specifically, I will discuss the equation that governs the voltage discharge of a capacitor over time. In an RC circuit, when a charged capacitor is allowed to discharge through a resistor, the voltage across the capacitor decreases exponentially. The relationship between the voltage V and time t is given by the following first-order differential equation. In this equation, V represents the voltage across the capacitor, R is the resistance, C is the capacitance, and T represents time. This equation describes how the voltage decays over time due to the resistor dissipating energy. Now, let's classify this differential equation based on its properties. First, this equation is classified as an ordinary differential equation because it has only one independent variable, which is t, that represents time. If it had multiple independent variables, it would be classified as a partial differential equation. And for example, the wave equation, partial squared u over partial t squared equals c squared times partial squared u over partial x squared, involve both time t and position x, making it a partial differential equation. Since our equation only depends on t, it is clearly an ordinary differential equation. Secondly, this is a first-order differential equation because the highest derivative present is dv over dt, which is a first derivative. If the equation contained a second derivative, such as d squared v over dt squared, then it will be classified as a second-order differential equation. However, since our equation only contains the first derivative, it falls under the first-order category. Next, we can see that this equation is linear because both v and its derivative appear in a linear form. There are no powers, products, or non-linear functions of v. If the functions were non-linear, it might look like this. Here, the presence of v squared makes it non-linear because it introduces a non-linearity in the relationship between v and its derivative. Since our given equation does not contain such non-linear terms, it is classified as a linear differential equation. Lastly, this is a homogeneous differential equation because all terms involve either the dependent variable v or its derivative dv over dt. The equation does not have any external function or constant term. For comparison, an example of a non-homogeneous equation would be like this, where ET represents an external voltage source. This equation would be non-homogeneous because ET is independent of V, meaning there is an external influence affecting the system. In conclusion, the voltage discharge equation in an RC circuit is an ordinary, first-order, linear, and homogeneous differential equation. Understanding this equation is important because it explains how capacitors release stored energy over time, which is crucial in electrical circuits. Thank you for listening.
Assalamualaikum and hi everyone. My name is QASEH BATRISYIA ZAILAL and my metric number is 228827. Today, I'm going to present about light hill rhythm research, also known as LWR model. It is a fundamental model in traffic flow theory that describes the movement of traffic as a continuous flow. It is widely used in transportation engineering, traffic simulation, and intelligent transportation systems. This model also helps us to understand how vehicles collectively behave on the road. It is also similar to how fluids flow in pipes. We can predict how traffic density changes over time based on the conservation of vehicles. As we can see, based on the formula given, rho is representing traffic density, which is number of cars per unit length at position x and time t, while v is representing velocity of vehicles at position x and time t. Now, let's move on to the classification of the equation. This equation is classified as partial differential equation, which is PDE, because it involves partial derivatives of traffic density, which is rho. with respect to multiple independent variables which to t, time, and x position. Based on the type of differential equation, this equation is a first-order PDE because the highest derivative is 1. Other than that, this equation is nonlinear. This is because velocity depends on traffic density rho. For example, when there are too many cars, they will slow down, which will change the value of velocity. If v is a constant, then the equation will be linear. This equation is homogeneous. This is because there is no external forcing term, as you can see on the right-hand side, which is 0. This indicates it is a conservation equation for traffic flow. This means cars only move from one place to another, and no cars are being destroyed or created within the system. Thank you. That's all from me.
Hello, my name is SITI ELYSA BINTI NOOR, and my metric number is 231119, and I'm from Group 1. I want to talk about heat conduction in an insulated wire in differential equation. As you can see, U in bracket xt, where U is the temperature function and x is the position, and where t is the time. And for x is a spatial coordinate, represent a position along the length of the wire. And for t is time variable, which represents how temperature evolves over time. And for k is thermal diffusivity, represent a constant depends on materials properties. For the classification of the equation, it is a partial differential equation (PDE), which is an equation that involves partial derivative of a function with respect to multiple independent variables such as del u per del t and del square u per del x square, rather than ordinary derivatives. For the second one, it is a second order partial differential equation, since as we know, the order of the PDE is determined by the highest order derivative present in the equation. Since the highest derivative in the equation is second order, as in del square u per del x square. And for the third one, it is a linear partial differential equation, since that it does not contain any nonlinear terms or products of u and its derivatives, such as u square or sine u. And for the last one, it is a homogeneous partial differential equation, since as we all know, the equation is homogeneous if there are no additional external forces or source terms, and as we can see in the equation, there is no additional terms on the hand right side. So, it is a homogeneous partial differential equation. Thank you. That's all from me.
Assalamualaikum and hello everyone. My name is AMIRAH QISTINA binti AZMEL and my number matrix is 229590. So today I would like to talk about why would we use differential equations in studying electromagnetic wave. We all know that we use technologies such as Wi-Fi, mobile phone, and satellite communications. But have you ever wondered how these signals go through and travel through space and to our device? This is where differential equations comes in. We all know that electromagnetic wave such as light wave, radio wave, and microwave just not appear out of nowhere, but it use mathematical equations described by Maxwell equations. That one was a set of differential equations that show us and describe how electric and magnetic field behave. Alright, so we will show you the equations of Maxwell. So, the question we see here is where E is the electric field strength, T is time, X is the spatial variable position along with the x-axis, and C is the speed of the wave, which is speed of light in the case of electromagnetic wave. These equations describe how electromagnetic waves propagate through space and interact with their movements. Alright, so move to classifications of the equations. We have 4 classifications. First is partial differential equations, PDE. It is derivative with respect to more than one variable, namely times and positions x. For the second one, second order differentiation equations. It contains second order derivative of electric field E, making it a second order equations. Third, it is linear because E and its derivative appear only in first power without any product or high power. For the last one is it is homogeneous because it contains no extra terms apart from E and its derivative.
Right, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad IRFAN from ZAMAR, the metric number 227573. And today I want to present about the application of differential equation in different domains. So the topic that I want to present on is about differential equation in motion. So as we know, when we talk about motion, we usually think about Newton's second law, which is force equals to mass times acceleration. The acceleration is just the secondary derivative of displacement, and by using this equation and apply it with different equation, we can get a new differential equation. So in this example, I'm using a spring motion equation. The equation here become m times d square x over dt square is equal to negative kx, where the x is the displacement of the object, t is the time taken, k is the spring constant, and the m is the mass of the object that being pulled by the spring. So about this equation, this differential equation is the second order equation because of the second derivative of d square x over dt square. The equation is also homogeneous ordinary differential equation. It is ordinary because of it only has one independent variable, which is t square, which is time taken. It's also homogeneous because of everything we put in the side will be equal to 0. And next is the equation is linear, where there is no variable that are being raised to the power of something. And yeah, that's all from me.